So what's up guys, this is Saish and you're watching Optimal Physics. This is the third part in the three-part series. The first topic, which is units, dimensions and measurements, are broken down into three parts, and this is the third part. We're going to talk in this chapter about significant figures, and then we're going to go into error analysis. So I hope you guys have watched the first two parts. So significant figures and error analysis. Most of the questions, as far as IIT exam is concerned, IIT mains, NEET. This is a very important topic. I mean, people can ask you questions in this. As far as the first two topics are concerned, they are mostly first two parts. They are mostly important from the board point of view because they can ask you subjective questions. But as far as numericals are concerned, significant figures and error analysis are the two very important sections in this chapter. So let's start. As you can see, I'm drinking my coffee also as I'm teaching you guys. I love coffee. I don't know about you guys, but even when I was studying, coffee was always my favorite. Whenever you have to sit late nights for studying, coffee really helps. Okay, so first let's start with what is significant figures. So what do you think is a significant figure? So as the name suggests, significant means kind of important. So we're interested here in knowing which figures in a number are important and which are not important. So I guess you guys would have been familiar with conducting experiments in the laboratory. You are conducting experiments, say. So I'm giving you a scenario here, and here is a rod, and you are interested. This is a rod, and you are interested in measuring the length of this rod. How long is this rod? And you use your vernier, or let's say you're using a scale, a meter scale. Okay, so meter scale will have a readings from centimeters. So at every centimeter, it's gonna have a mark. 1 centimeter, 2 centimeter. Here I will write say 3 centimeter, 4 centimeters, and well, I should improve on my drawing skills. But anyway, so and each centimeter is divided into 10. You know, so there are 10 divisions, and we call each of them as a millimeter, right? Now, what you do is when you're given a scale like this, you will take the scale and you will match the zero of the scale with one end of the rod, Hana. So I'll just redraw the rod so that you understand. So you will take your rod, whatever this rod, you will match the zero of this with the zero, with one end of the rod, right? And you will see where the other end of the rod lies. Now let's say the rod end lies somewhere here. Okay. Now we know it is 3 point something. So what you will do next is you will go and measure the next. यहाँ पे क्या whatever is the next thing here. Here it may be the 3.1 का mark. So 3.1 centimeters. This is 0.1 means it is 1 mm, and here there is 3.2 centimeters. So what you will do is your rod's end lies somewhere between 3.1 and 3.2, and now there is an uncertainty there. So what will happen is you have to figure out exactly. So as you can see, I'm using Hindi in between. I hope you guys will understand, but it's mostly an English based channel, so I'll sometimes use Hindi in between. But yeah, so I was here. See that's so I was telling you about the end of this rod lies somewhere between 3.1 and 3.2 centimeters. So I will mentally divide this 3.1 and 3.2 between again some 10 units, say, and I will say this is approximately around 3.13, let's say. So if I divide this between again 10 intervals, 3.11, 3.12, 3.13, and till that 3.2, I'll say this end lies somewhere around 3.13 centimeters, and I'll write this number. Now you'll see that this 3 which I wrote here at the end, it's 3.13. Now this 3 at the end I was really not that sure about this 3, and we call this as the most uncertain digit. Okay, or it is also like the least accurate digit, and we will say 3, which we were so confident that it is, we are confident like 3 is, it's about 3, I mean it's somewhere between 3.1 and 3.2, but we are just not sure whether it is 3.12, 13. We don't know about this 3, so we will see 3, we will report the dimension as 3, we will write the unit as 3 point, or we will write the measurement as 3.1 3 centimeters. Now, this is the most doubtful and this is the least doubtful, right? So all these digits which are most doubtful as well as least doubtful, and all the digits within that, we consider them to be all significant. So there are like 3 significant figures in this number. Okay. Now, when I give any number to you, for example, 3.03, 3.300, we are here interested in knowing how many digits, how many significant figures does this number have, how many significant figures does this number have. There are certain rules to figure out how to find significant figures, and that's what we're going to talk about now. So next we're going to talk about the rules for significant digits. I'll write SD. So the first rule that will help you. Now these are rules which are like only 5. There are only 4 rules which you have to know, and based on that, given any number, you will be able to find whether how many significant figures or how many significant digits is the same thing. Significant digits. How many significant digits are there in that number? So the first rule says all non-zero digits are significant. And what does that mean? For example, I give you a number, something like 145. Now all the digits are non-zero digits here, so they're significant, right? 1.134. Even if there is a decimal point, all that you're interested in knowing is whether the digit is 0 or non-zero. So if you find a digit is non-zero, it is significant. So this has 1, 2, 3, 4. This has 4 significant figures, significant digits. I will use significant digits SD as far as this lecture is concerned. This number has 3 significant digits. So that's all about first rule, which says all non-zero digits are significant. Okay. Now let's talk about the next rule. So the next rule says, I'll go in that order, I jotted down. So it says all the zeros between 2 significant digits are always significant. All the zeros between 2 significant digits are significant. Now what does this mean? For example, if I write a number like 1.045, how many significant digits are there in this number? This is a typical question which you will be given. Okay. Now 1, this is a non-zero digit, so it is significant. Same with the 4 and 5. Now here I see this is significant, and there is a 0 which is between them. Hence this 0 is considered to be significant. Right. So this number has 4 significant digits. Whenever you find a 0 between any 2 numbers, any 2 significant digits, it is significant. Even something like 103, 100025. The 2 numbers I have given you, 103 and 100025. So we see this is significant, these 3 zeros are lying between these 2 significant digits, hence they are significant. So this number has 1, 2, 3, 4, 5, 6, total 6 significant digits. What about 103? 1 is significant, 3 is significant, 0 is lying between them, hence this 0 is also significant. So there are 3 significant digits here. So this is all about the second rule, which says the zeros between two significant digits are significant. Now this is applicable even if there is a decimal point. So moment you find there is a zero between two significant digits, it is significant. That's all you need to know. Let's move on to the third rule. I'll take some problems at the end, some basic whether how many significant digits are there in this number kind of problems, which will help you to understand how do you apply this rule. The third is, in a decimal portion, only the trailing zeros are significant. Okay, so what does this mean? So let me take a number 1.500. Now these two zeros are coming at the end, right? These are what we call as trailing zeros. That means they are at the end of the end of this number, and they are coming after a decimal point. So I mentioned here trailing zeros in a decimal portion. So when I'm saying decimal portion, this is the decimal portion, numbers that are following after the decimal point. So these two zeros are significant. So trailing zeros are always significant in any number, but provided they are coming after decimal point. Okay, let's take another example. 5.0300100. Okay, now how many significant digits are there in this number? This would be a typical question. So 5, the non-zero digits, significant, this is significant, this is significant. This 0 is coming between two non-zero digits, rule number 2, hence significant. Same for here, this is also significant. These two are trailing zeros, hence they are also significant. Now, these are three basic rules, and there is one more rule which I will talk about it in a bit later. But now we'll talk about zeros, because zeros are the most confusing. Now I said trailing zeros are significant, which means whenever there is no trailing zero and these zeros are at some other location, then they are not significant. Let me give you an example. So let's say 0.00500. Okay. Now 5 is significant, of course. What about 0? These two are trailing zeros, so they are significant, as I told you already. What about these two zeros? They are not lying between any non-zero digits. Same with, they are not lying between any two significant digits. Same with this. So if there is a decimal and if there is a 0, if the number is less than 1 and it is like 0 point something, the 0 which follows here is not significant. Same with these zeros. These zeros are not significant. They are not trailing zeros, right? So these zeros are not significant. So I will give you some examples. Let's say 0.040340. How many significant figures are there in this number? This is a trailing zero, significant. 3, 4, 4, they are significant. What about this zero? This is lying between two significant digits, hence this is also significant. What about this? I told you just now, this is not significant. Same with this is not significant. It is not a trailing zero and it is not lying between any two significant digits. So hence this is not significant. So this number has 1, 2, 3, 4, 5. So 5 significant digits. Okay. Now if I give you a number like 5.00, what about this number? 5 significant, after decimal point 2 zeros, significant. What about this 0? This 0 is not significant. Okay, everybody okay with this? I hope that I was very clear with this. Now rule number 4 is power of 10 is not significant. Now what do I mean by that? If I give you any number, something like 4.01 into 10 to the power 5. Now this 10 to the power 5, there are 5 zeros here. This does not count in significant digits. So we are only interested in this portion. So whenever you see something like this is usually what we call a scientific notation. So this trailing zeros, not trailing zeros, so this is a power of 10. So power of 10 is not significant at all. So we're not supposed to count any significant figures here. So 4.01 has just 3 significant figures here. Now when you are interested in reporting a measurement, say 2.0 into 10 to the power 6 and 2.00 into 10 to the power 6 and 2.000 into 10 to the power 6. Now all three of them, though they have the same value, the significant figures are different. Okay, now it depends on the way you are writing it. Okay, so here after decimal point I have 1 0, I have put 2 zeros, I have put 3 zeros, and there is a reason why someone would do that when they're reporting a reading. So as I told you, if I ask you significant digits in this number, use the same logic. 10 raised to 6, no significant figures. What about here? Here there are two significant figures, right? What about this? These two are trailing zeros. They are coming after decimal point. Hence they are significant. So there are three significant digits. Here there are 4. So I hope this concept is very clear by now. So how do you find significant figures in a particular number? So you will be asked, typically you will be given a number and asked to find how many significant figures are there in that number. You should be applying these rules, and that will help you to find significant figures. Okay, so guys, now let's look into how are we going to perform operations with these significant figures. So you will come across these situations wherein you need to add two significant figures, you need to add two measurements. So how do you go about doing that? So let's say, for example, there is one rod whose length I find. Let me draw a better one. So this is the first rod A. There is another rod B, which is longer than this, and I find, say, the length of this rod to be 2.03 meters. Okay, and as far as rod B is concerned, I'm able to make even more precise measurements, and I say I could find the length of this rod to be not 2. Let's take it. It looks bigger. And let's say this is 5.004. So you can see here I could find the measurement, of course meter. Here I could find it up to 0.03, that is up to 2 decimal places. Now I could find it up to 3 decimal places. Now if I were to ask you what is the length, what if I combine these two rods A plus B, what will be the total length of this rod? And how would you do that? I mean, the obvious way would be, you would add this plus this, 5.004 plus 2.03, that will give you 7.034 meter, right? But this is not the right way to report the quantities, because this actually misleads us. It tells you that if you add both of them, you are able to find the sum to 3 decimal places. That's what, when you write something like this, it shows that you are able to find the number up to 3rd decimal place, which is not the case. Actually, the reality is only the rod B was found to be precise up to 3rd decimal place, whereas rod A was only up to 2 decimal places. So when you're reporting the final answer, if you write something like 7.034, it gives a wrong representation that you are able to find the last digit here to the 3rd decimal place, which is not the case. So what we do is, in that case, we find this is only precise up to 2 decimal places. So there are 2 significant figures here after decimal place. So we find the number of significant figures after the decimal place. So in rod A, there are 2 significant figures after decimal place. Here there are 3 significant figures after decimal place. So we choose the least of these 2 and report the answer up to 2 significant figures after decimal place. So I have to report it to this number, right? So if I were to round it up, it's going to be 7.03 meters. So, well, that brings me to another point, like how do you go about rounding? Now, I have rounded this number 7.034 to 7.03 because I was supposed to round it to 2 decimal places. So I've eliminated this 4, but there is a rule that you need to understand. There are some basic rules of rounding off. I'm going to go through that. Rounding digits. So if I give you any number, let's start with an example. I'll tell you 7.294. Okay, and I want to round this number. This is a number which is given to you, and I want to round this to 3 significant figures. So as you can see, this number now has 1, 2, 3, 4, 4 significant digits. And if I tell you to round it to 3 significant digits, that means I need to trim this portion. I need to only report 1, 2, 3, these 3 digits. So what you do is you look at the number to be rounded. So this number is to be rounded. You look at the number after that. So now this is 4. If this number which follows the number to be rounded, listen to this carefully. If this number is less than 5, you keep this number unchanged. So this, if I were to round this off, it's going to be just 7.29. Okay. Now, if this number, instead of 4, it was a number which was greater than 5, then you add 1 to this number. Okay. So if I give you, say, another example, let me take another example. If I give you, say, 7.288, okay, and I need to round this number to, this is the number, it has 4 significant digits, I need to round it to, say, 3 significant digits, only till this portion. I look at a number which follows the number to be rounded. So that is 8, which is greater than 5. So I'm going to add 1 to this number and report my answer as 7.29. Now what do you do if this number is 5? So there are 2 ways. 7.285. What do you do in this case? And if you were to round it up to 3 significant digits, what you do in that case is you look at this number. If this number is even, you leave this number unchanged. And if this number turns out to be odd, you add 1 to that number. So if in this case, if I were to round it to this 3 digits, since there is a 5 here, I will use this rule. I will say this number which is 8, which is even, so I'm going to leave it unchanged, and it's going to be 7.28. Okay. Now if instead of 8, if this number was 7.275, and I need to round it off till this portion, since there is a 5 which is following, what I would do is I will ask the question, what about this number? This number is odd, so I'm going to add 1 to it, and I'm going to say 7.28. Okay, so this was about rounding off these digits. So we covered the first. Let's go back and continue the discussion about operations. So we talked about addition and subtraction. Now let's talk about multiplication and division. So in addition and subtraction, we were interested in looking at the significant digits after the decimal point, and we found which number has the least significant digits after decimal point, and the answer that we reported was having that least number of significant figures after decimal point. So that I made it clear through an example. Now let's talk about multiplication and division. In this case, it is very straightforward. So if I give you two numbers, say 7.23 and 3.0, how do you go about? And if I tell you these 2 numbers that we multiplied, report the final answer. And what you do is you count the significant digits in this number. 2 significant digits. Here there are 3 significant digits. So you just multiply this number like you would do normally. So this number would be how much? 9, and this is gonna be right 21.69 zeros. I can add whatever it is, but now we're interested in answering this question. So there are 2 significant digits here, so I need to report my answer two significant digits only. So here there are three significant digits, here there are two significant digits. So I need to round this off to these two digits. How am I going to do? Simple. There is a decimal point here and its number is 6. So I should increase this by 1. So I'm going to say this answer is 22. Right? So I use this rule for rounding, which I just talked about in the previous section. So the rule here is to report the answer to the in the significant figures which has the least number of significant figures. So this number has 3 significant figures, this has 2 significant figures. My answer should have 2 significant figures. As simple as that. So the answer is 22, which is 2 significant figures. Okay. Same applies with division. You just perform the normal division, and then the answer that you will be reporting will be having the least significant figures as it is in one of the numbers. So that was about the significant figures and operations with significant figures. So what's up, guys? Now we will start with the next topic, which is error analysis. Okay, let's try to understand what exactly is error and why should we even study about error. So while conducting experiments, you would have seen that any number that you report, say you report a reading as say 2.54, you are not really sure whether the number is 2.54. It could be 2.53 or it could be 2.55, right? So this could be due to many reasons. One common reason is due to human errors. You look at a particular scale from one direction, you will say it's to be 2.53, and from the other direction you may say it's 2.55. So this is what you call as a human error. Now, so in any experiment that you do, there's gonna be error. Now, what we do is we usually broadly classify error into two categories. So one type of error is what we call as systematic error, and the other one is called as random error. And what exactly the systematic error? The systematic error arises because of the faulty instruments. So there are cases wherein you will have a particular weighing scale, and even if you don't place anything on that scale, the scale is going to still give you some reading. Say the scale gives you a reading of 10 grams. So when you're placing an object which is say 40 grams, it's going to show you 40 grams plus 10 grams, because the scale itself shows a reading of 10 grams when you don't place anything. So in such a case, we say the instrument has an inbuilt error in it, and that's what we call a systematic error. We say it's systematic error because the error is in the system, and we know this error. Now this could be due to any other reason, for right. Now in contrast to this, there could be random errors. Now random errors could be due to many reasons. Like one common random error is the human error. While measuring the instrument, I just told you, you observe it from two different directions, and one guy reports the reading as 2.53, other one says it's 2.55. It's a human error. Now it could also happen that some other things, environmental changes happen, like the wind blows very fast while performing an experiment, and you really have no control over this factors. That's why we call them random errors. We really don't know what are the causes of this. Usually systematic errors, we know the cause and it's a fixed value, and so before performing the experiment, you know that there is an error in the system, so you can add that error to that experiment. Whereas random error, you really don't know about the value. Now so now you have a feel of what exactly is error. It's basically you're supposed to measure something and you're expecting some reading, but readings are gonna be around that number, because of so many errors. So one way of putting that is, let me try to define error. So before that, let me define something called as true value. True value is the actual value. Now in many cases you really don't know about true value, but say you are expected to get certain value for a particular physical quantity, and you end up obtaining something else. That true value represents what you are expected to obtain. Okay, in some cases it is known, and in some cases I'll tell you how you go about finding the true value. So true value is the actual value of the physical quantity which you're trying to measure, and what you are measuring is called as a measured value. Now these things will become clear in a while. So the error then is defined as the difference between true value and measured value. Okay. Now this number could be positive or negative. Okay, it could be both. It depends. If your true value, it could be lesser or higher. So this number could be both positive or negative. So error is defined as the difference between true value and the measured value. Okay. Now what exactly is a true value? So as we talked about before, it's when it comes to error, our goal should be to minimize this error as much as possible. So whenever you're conducting any experiment, you don't want the error to be high, you want the error to be as low as possible, right? So in order to do that, what we do is we conduct we take number of readings, we conduct the same experiment a number of times, and you report a particular value for n different readings. So let's say you're performing an experiment in which you're supposed to take readings, and you do that experiment n number of times. Okay. In the first experiment, you get a reading as R1, next you get R2, like this. You're doing it n times, so you get Rn as Rn readings. These are total number of readings. You get n readings basically. Now, I want to find what is the best possible value for that physical quantity. So what I do is I take the R average. So I add all of them, all the readings which I obtained till Rn, and divided by the number of readings which you took. So this number is way more accurate. I mean, if I were to report a reading for a particular experiment, rather than reporting R1, R2, R3, I got different values, right? Each time I conducted the experiment, I would report R average, because now this is like the much better way of measuring this, R's. So because I got the average, it always represents something which is like you're taken all the numbers, you divided by n, so it represents the best possible value for that particular physical quantity. So R average would be the reading that I would report. Now, that's not the way actually you go about representing. You should always represent it. You should also always report it with an error. So what we do is we find the error in next. What we'll do is, now that we know R average, we'll try to find error in each experiment. So for the first experiment which we did, I got a value of R1 as my reading. Now I will say R average, I will set it to be my true value. Now I talked about error, definition of error as true value minus measured value, and I told you that true value is, we will be defining later. So here is a definition. So what I will say is, this R average which I found by summing all these numbers and dividing it by n, I will say that to be the true value. Okay, and now I will subtract, this really doesn't, because I am going to put a mod sign, so R1 minus R average. So I am going to subtract R average from the first reading and take the modulus. That's going to give me absolute error. This is what I call as the absolute error in reading 1. I will say that again. So what I did is I found R average, I subtracted R average from the first reading, took the modulus, so that I don't have, I mean, this could be positive or negative. So when I take the modulus, it's always positive. So that becomes my absolute error. This is what I call as absolute error in the reading 1. I do that for all the experiments. For the experiment 2, I will say R2 minus R average, and that will be delta R2, absolute error in reading 2. So I'll do that for all the readings, and then what I will do is, I will drop this. I'll define mean average error, delta R average, yes, delta R1 plus delta R2 till delta Rn, and divide it with n. So this is error, and you take the mean of those absolute errors. So you sum it all and divide it by n. So that is what is your delta R average. So now when I have to report my final reading, I report it as R average plus or minus delta R average, which means this is the true value which I obtained, and this is the error in my experiment, delta R average. Right? I don't want to say write as delta R1, delta R2 here. Delta R average represents a whole. I mean, you are taking the average of all the n quantities, so it is a much better way to represent the error, isn't it? So this is how we report a particular error. So I'll write it down again. So you will be reporting your reading R as R average plus or minus delta R average. Okay. Now, in some cases, you will represent it with percentage error. Now, I'll tell you what exactly you mean by percentage error. Percentage error is defined as delta R average divided by R average. You multiply it with 100. It's very simple. It's just the way you represent it. So, I'll just give you an example. I could find a resistance of a wire as 6 ohms plus or minus zero point 0.6. Okay. Now in this case 6 ohm represents the average value plus or minus zero point 0.6. So what is the percentage error here? Percentage error is 0.6 by 6 into 100, which is 10%. So in some cases, if instead of 6 plus or minus 0.6 ohm, they will also write it as 6 plus or minus 10%, which means you should understand it is 10% of 6. So you should be able to convert these two things back and forth. Okay. Now we'll talk about operations. So how is error? How does error propagate? So it will be called as propagation of error. Now why do we need that? Because whenever you are measuring a particular quantity, and it will depend on two different quantities. For example, you could measure, say, the speed of an object, and it depends on the distance and time, right? So when you're measuring a distance, there could be an error in the measurement. So you could measure it as 20 plus or minus zero point 0.2 meters, and time also you could be an error. So you could have error in your clock. So you can also have time. You can measure it maybe as 5 seconds plus or minus 0.05 seconds, right? Now how do we go about finding speed? Because this top numerator has some error, denominator also has some error. So how do you go about doing this thing? That's what I call by propagation of error. So I will divide into two parts. The first one is how do you go about error propagation when it comes to addition or subtraction. And by that, what I mean is, if I give you one quantity A and there's another quantity B, quantity A could be something like, say, resistance of a wire, like 6 ohms plus or minus zero point 0.6 ohm, and this could be again some other resistance like 8 ohms plus or minus zero point 0.4 ohms. Now, if I tell you if this resistance A and resistance B are connected in series, you get A plus B, right? So what is the total error in the overall resistance? So now you are adding this quantity and you are adding another quantity. Each of them has an error. So what happens is, one thing you need to remember, whether it is addition or subtraction, error is always added. Okay, I'll write it here. It's always added. Okay, so sometimes people make mistake that when they're subtracting, they subtract error also, which is not the case. So in terms of in the first case, now we'll talk about error in A plus B. A plus B, the value will be 8 plus 6, 14. Okay, sorry. So 8 plus 6, 14, plus or minus, you're going to add both of them. So that's going to be 0.6 plus 0.4, that's 1. Okay, so that is what we call as the that is how you do the error operations when it comes to addition. Even if it would be have been a minus b, I mean it could be some other quantity, then also you would be adding. If it is say a minus b, then it would be, or b minus a, say. So if it would have been b minus a, if you are subtracting two quantities with quantity b having an error of zero point 0.4 and quantity a having an error of 0.6, the error will always be added. It will be 1 ohm and it will be 2 plus or minus 1 ohm. Okay, so that is how you carry the addition and subtraction. Let's talk about the next one, that is multiplication and division. Now when it comes to multiplication and division, so let's take an example. There is an x first quantity, which is basically say x plus or minus delta x, and you have another quantity y, which is y plus or minus delta y. So I won't go into derivation of how should you go about doing this, but I'll give you the final formula, or the most important. I'll talk about the most important part here. So what you should be doing is, when it comes to multiplication or division, first convert this x to percentage error form. So you're going to write this as x plus or minus delta x by x into 100%. This is how we write the percentage error, right? So I told you delta x is the absolute error here. You divide it with the true value and multiply by 100. That is going to give you percentage error. So this represents percentage error in x. Similarly, you do it for y, so which is delta y by y into 100%. This represents percentage error in y. Now if I ask you x into y, what would be the error? You just multiply these two quantities as it is, xy. Okay, as far as error is concerned, it would be plus or minus, just add these two quantities, add the percentage error in x plus percentage error in y. That would be the percentage error in the total xy quantity. Now I'll explain that through an example. So but I'll do that later. So it's the same thing in case of, even when you're dividing say x by y, what you'll be doing is you'll be dividing x by y, and plus or minus you'll be adding the percentage error in x, percentage error in y, and that would be a percentage error in this whole quantity x by y. So note that you are not getting the absolute error here. This error is a percentage error in xy, the product xy. So I'll give you an example. Let's say x is equal to 6 plus or minus 0.6 ohm. Okay, so I'll convert into percentage form. This is 6 plus or minus 0.6 by 6 into 100, 10%. Y is say 8 plus or minus 0.4 ohms. I'll convert into percentage form. 8 plus or minus 0.4 by 8 into 100. How much is it? I think it's 5%, right? 0.4 by, yeah, so yeah, it's 5%. I don't know why it took so long for me. X into y would be, you multiply these two first, 48 plus or minus 10% plus 15%. 15%. Remember this. So if I were to write the quantity xy, it would be 48 plus or minus 15 by 48 into 100. This is the absolute error now. Okay. So same with x by y. X by y would have been 6 by 8 plus or minus 15%. Okay. Now we'll talk about powers, which is which is a very commonly asked question. So for example, they will give you a quantity, say x, which depend on many other quantities, a raised to m, b raised to n, or c raised to p, say. And you know errors, a is basically represented as a plus or minus delta a, b is having an error of delta b, and c is having an error of delta c. So in all these type of questions, what you should be doing is first convert all these quantities a, p, c into a percentage forms. Okay, so percentage, you will write it as a plus or minus percentage error in a, same for b, same for c. So you now know the percentage error in each one of them. Okay, now as far as this operation is concerned, what you will be doing is x would be, you carry out this operation a raised to m, b raised to, I mean this is the number, don't first ignore all the error terms and just carry out this operation a raised to m, b raised to n by c raised to p. So it will be a small a raised to m into b the small b raised to n by c raised to p, and that will be your number, and there will be an error term, right? Now what is that error term? We'll calculate it. So the formula is percentage error in x, okay, would be equal to m times percentage error in a plus n times percentage error in b plus p times percentage error in c. I'll write it neatly again because people might get confused. So if you're given something like this, okay, and you are interested in knowing what is the percentage error in x, that is equal to m times percentage error in a plus n times percentage error in b plus p times percentage error in c. So you will see that I am taking the power m, multiplying it by percentage error with that particular quantity. So a has a percentage error of say 8%. So m times 8% plus b has a percentage error say of say 6%, and this power is say 3. So 3 times percentage error in b plus q. Now there is a, even though the c is in the denominator and it's a division, it is error is always added. Okay, you don't subtract error at all. So this is the formula for finding percentage error in the quantity which depends on many other quantities a, b and c. So here it is, percentage error is always added, and if they are raised to some, if they have quantities in which the individual quantities are raised to some power, you will be multiplying with that particular power the percentage error in that particular quantity. Okay, let's do a quick problem. So I'll say a quantity x depends on a is defined as a square b cube by c raised to 5, and quantity a has a percentage error of say 5%, quantity b has a percentage error of say 2%, and c has a percentage error of say 1%. So what would be the percentage error in x? What I would do is 2 times percentage error in a is the same formula, 3 times percentage error in b plus 5 times percentage error in c. Let me substitute that. 2 times percentage error in a is 5 plus 3 times percentage error in b is 2 plus 5 times percentage error in c is 1. So this will be the total error. 10 plus 6 plus 5, that is 21. So x is going to have a percentage error of 21. So you can see that though these quantities have 5, 2 and 1, the final quantity x, since it depends on the powers, c is raised to 5, a is raised to 2 and b is raised to 3, it ended up having a percentage error of such a huge number. Okay, that was all about errors, guys. I hope you liked this lecture. Do comment below and subscribe to my channel. If you want to hear more of this, do share with other people who will find it interesting. So next topic will be kinematics. Okay, so in which I'll cover motion in straight line, average velocities, things like that. So today's lecture I've completed the third part of the first chapter. So we covered systematic significant figures, and we also covered error analysis. That was it, guys. So I hope you liked it. I'll see you guys in the next video. Till then, bye bye.